Hi. Hi everyone. So there's a good question posted in the chat about should should people, what was it? Should people can I post the output of my program for assignment 1 in ed? So the answer I have to this question is basically yes, because I like if I said no, what people would do is share it privately with their friends. And if that happened, again, I'm basically going to be punishing people without friends. So, like, rather than say no and try and make you all do your own work, I'd rather just say yes so that people share it in a more public forum so that people. When I say without friends, I just mean like without friends in this course kind of thing, right? Um, so yeah, that people without friends in this course can, just like everyone's sad in the chat. It's like they're posting me like hi. Yeah, it's just I don't like inequity where we can avoid it easily. So yeah, let's get on to the next part, which is STL iterators. STL iterators, which is a fun little topic. Okay. All right. So STL iterators. We understand what a pointer is because of our basic C knowledge. An iterator, though, is something in the past you might have referred to as a variable called I that was an int that you iterated through an array with or something, right? But in C++ and many other languages, an iterator is an abstract notion of a pointer. Now, what that means is that it feels, it behaves, it like sounds, it smells like a pointer, but it's still an abstraction of a pointer. And we'll get to that more. But at its most fundamental level, iterators are types that abstract containers have, basically all those containers we talked about, that try and abstract that container to a linear sequence of objects. So what I mean by that is that whether you have a vector or a linked list or a doubly linked list or a map, which is a binary tree, or an unordered map, which is a hash map, it's trying to reduce all of those containers down to a common type, which is a sequence. It essentially behaves like a list or array that you go tick, 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 tick through in like a linear fashion. So it's a nice common generic abstraction with that. And what this allows us to do is to basically take an algorithm like, say, a search algorithm, or say search algorithm that would, like a linear search, say, and we can do a linear search. We can use the same algorithm on a vector, we can use it on an array, we can use it on some kind of hash map, some kind of tree structure, we can use it on all of those things. So it's trying to standardize how all of that works. Elon says point of it in object form. I guess so. Like in a lot of ways, it is an object, kind of like a pointer, but like we'll get to that. So how this actually works in C++, we talked about this before, is that when you have a container, where in this case A is like say a vector, right? A vector array, it doesn't matter. When you ask for a.begin, what you're asking for is a abstract pointer to the first element of that container as you're iterating through it. When you ask for a.end, what you're asking for is for a abstract pointer to one after the end of that structure. Okay? And it's not actually pointing to a real value. That's like the most important part here. Now, the iterators that you deal with behave like pointers. So you have to claw back to your pointer brain for a second here to figure that out. And as you loop through this, you'll see that we have these variables here like iter. We say that our iterator is equal to names.begin. And we're going to loop while our iterator is not equal to names.end. And each time we loop, we're going to increase our iterator by 1. And you can see here, every time we loop, we're printing out star iter. So what does star iter mean? Well, star iter is dereference iter. So if you were using raw pointers, it would be, we're going to take our pointer and we're going to dereference it, i.e. get the value at the address that pointer points to. And that's how we get the value. And you can also increment it. So what we're actually doing here is, in theory, like incrementing a pointer, like moving it up one memory address. And here we're saying, oh, we're going to get the value at that pointer. The difference is this is not an actual pointer. It's not a literal address in memory. It's an object, as Elon kind of said, which abstracts it, which gives us a couple of protections and a few useful things, but generally speaking, you should assume its behavior as like a pointer. Using iterators is, yeah, it's so there's a couple of questions about like, oh, like I can feel the tone as like, and this kind of seems very like anti-pattern, seems very like C style. Can we use references? Is this really good practice? So first thing I'd say is if you were just looping through an array to print something out, you're probably just going to use a for range loop, or you're going to use an algorithm. Generally speaking, you don't actually interact much with the pointer directly. But so this kind of example is not the best one to explain a common case, but we'll keep talking about that. So that's an important thing. Now we're going to look at this piece of code because this demonstrates it really well. You can also see here that names.begin, when we use auto on that, it actually like the type that it is set to is actually not, it's a standard vector of standard string, which is what the containers type is, iterator type. So that iterator type is defined in the vector library, and typically you never really define those explicitly. It's always kind of defined through auto. And then Quinjian says, how do we retrieve the index using iterator? That's a great question. So you can't, and the reason you can't is because an index, when you're iterating through something, an index kind of implies a location. Like, if you're iterating through an array, an index means something because the array's contiguous. If you're iterating through a linked list, the index doesn't really mean a lot because the linked list might be implemented really differently, or a tree. Like, what's the index of a tree node? What's the index of a hash map thing? Like, it doesn't always mean something. Like, it might mean something in the case of this vector, sure, but for all the other types of containers that don't have contiguous memory, an index doesn't really mean a lot. So that's what I mean about an iterator as a way to abstractly linearize a container and just like go through each element one by one, even if there's no real sense of even if there's no like real sense of order, like contiguous order. So let's go to lecture 204. If you need to use index, you track it separately. So I've got this vector called names, which I didn't populate for some reason. But let's do that now, and let's use the new structure. Auto names equals standard vector, standard string, and we'll do like, you know, hi, how are you? Like that, right? Those 4 things. Now let's try and build and run this one. So we'll build 204. Perfect. Then we'll run it. Hi, how are you? Hi, how are you? Right? So printed it out twice. Now we don't need this bottom one here at all. So here's a few of the things I want to take you through with iterators. It's actually on the next slide anyway, so I'm kind of jumping slightly ahead here, but I think this is an easier way to demonstrate it. Yeah. I guess it's very confusing code that I've called my vector names. Oh, look, I'll call it words then, alright? Oh god, I just closed the file. Yep, I'll call it words for you. There you go, words. Now, sorry, I was just checking something. Okay, so you can see when we print this out, it prints out what you'd expect. It says, hi, how are you? Now, there's a few other ways we can use iterators. So if I go back to standard vector in Google, you'll see that there's a bunch of iterator methods. Here we have begin and C begin, we have end and C end, we have R begin and CR begin, and we have R end and CR end. Now, the way that's structured is it might be a little bit confusing, but generally speaking, we have begin and end, we have R begin and R end, we have C begin and C end, and then we have CR begin and CR end. Now, what all these things mean is pretty simple. R means reverse, C means const. That's it. When we loop through something in the other direction, we can simply put R begin and R end here. And I'll build this again, 204, and we will run it. And you'll see that it's been printed out now in the reverse order. So, conceptually, what's happened here? Well, let's go back to our slides. What's happened here is that we have now, when we've said vec.begin previously, it's given us the first element, and then vec.end has given us one after the end. And when we ask for rbegin, we actually get the last element, and when we give rend, the rend is now one before the first element. Now, that should probably make some sense, right? The diagram's not super complicated, but what I really want to iterate here is, no pun intended, is that this method, the loop itself, has no real sense that it's going through the container backwards, right? As far, like, iterators always work the same thing. It's a linear abstract list that goes from the start to the finish. That's all it knows. That's all it knows here. It's all it knew before. The only difference is that in what way is the iterator quietly actually iterating through it? So what's happening here is this list kind of has the sense of like it's going like, you know, from left to right, like, you know, da, 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 da. But in reality, even though it's going left to right, the iterator itself's kind of going the opposite direction. And this is really cool because this iterator provides a really powerful abstraction where like your code does not need to worry about whether it's going forwards or backwards. You're just providing the iterator that will give you the linear abstraction in the way you want. Sarush asks a great question that might be on some people's minds, which is if the data structure is not contiguous in memory, maybe like an unordered set or a map, which we talked about was a tree, how does the iterator make a linear sense of it? Well, that's a good question. And we talk about this in week 7 in the course, and basically that's actually part of the job of the container. So the container implements the iterator. So even though we're like containers, algorithms, and iterators, containers are something on top of, iterators are something on top of containers that allow them to be linearized. So you know how when you do like, again, like data structures and algorithms, you get like a binary tree, right? And they do something like, you know, in order traversal, right? Where you have your binary tree and they, and they kind of teach you how to like print it out. Oh, in order is the wrong, in order? That's not an in order traversal, is it? Or is it? I thought that was pre-order. Anyway, maybe I'm crazy. Probably crazy. So like what actually happens is if you have a binary tree, you know that you can write a really simple recursive traversal algorithm that will print it out. I see what you're saying. Okay, thank you. I was like really confused. It is in order, it's just not a sorted binary tree. Yeah, you could write a recursive algorithm that would take a binary tree and just print it out in order by like iterating through it the right way. You could write that recursively, you could write it iteratively, but what an iterator does for a map, which we know is a sorted associative container, which is a tree underneath, it does that for you, right? So instead of you printing that tree out linearly, like the container itself, when it gives someone the iterator, it knows how to go through its tree, so it hides from the algorithm what's actually happening. So as far as the algorithm's concerned on the outside, it's like, oh, this is a nice linear list, but the container itself is providing it. So by putting the emphasis to every container that you have to provide me the ability to linearly go through your data structure, it then means that we can generalize our data structures across a whole range of algorithms. So rbegin, rn moves in the opposite direction. Then you also have crbegin and crend. Now, cbegin and cend and whatever, they're the const version of it. And a const iterator restricts you from modifying the element that it's abstractly pointing to. So for instance here, this is just a standard rbegin, rend. I could say, I can't remember how to do this in C++, but like, how do you make a string uppercase? Is it just string.upper or something? What is the... Someone will know because they've two upper. That's a C thing. Standard upper, great. Sorry guys, I'm sure some of you have already told me, and the YouTube lag and stuff is well behind because no one's answered it. It always comes through in a sec. It's like, oh hello. So yeah, you know, if I want to do this, I can just like, maybe no one told me. Okay. I can just include CC type. On this topic, actually, someone asked earlier in the lecture, I never got around to answering the question. They were like, should I include, if I'm using standard pair, should I hash include standard utility? The short answer is probably yes. What I would say is that every time you use an std : something that you didn't write, give it a quick look up on CPP reference, look at the library it's from, and hash include that in your code, and then you're all good. So I got CC type here now. I'm going to make this standard 2 upper iter. So I'm basically saying that it is a pointer, so dereferences the value, and I'm trying to make them all uppercase. Let's see if this works. Oh, I have an error. What's the error? No matching function called from 2 upper. What have I done? Oh, is there no std? Oh, this is for character. Oh, you guys are meant to look after me. Damn. Okay. I'm sure there's a string method. Let's just look up string. Maybe there's not. Probably not actually. C++ has a fairly simple string library compared to other languages, but that's okay. Let's just append it with something. I'm just reading the chat. So, is this sum iterator container begin consider a good way to calculate index when we need to do this? Index looping is a better choice. If you really need the index, then you would probably try and iterate through the iterator directly if it was a ordered container, like a sequence container, like an array. But if it was like another type of container, you'd probably just keep an index separately and then just increment it as you loop through it. That's probably what you would do, I would guess. Anyway, what string methods we have? Let's just find a random string method. I'm on c++.com, which we know we don't like. We'll just add something to the end of it. Can you concatenate with strings? I can't remember. Or we could replace them. Let's just do that. Hello. We could replace all the words with hello. And we run it, and now they're all hello. So one other useful thing about iterators is, you know, you can modify things a bit easier with it sometimes. You can do that with for range references as well. You can't hear. I don't know why you can't hear. I'm sorry. I think everyone can hear, but I'm just going to assume everyone can hear unless more people tell me. But so the thing is, though, if you used cbegin and cend, this would now not compile. So it will be a compile time error. You'll see this here. So where's the actual error? Not the BS that follows it. Here we go. No viable overload equals. Now this is a really obscure kind of error, which will hopefully make more sense when we talk about operator overloading. But basically what this is saying is that every type has a set of operators that you can use, right? Like an int, you can times and divide and plus and minus, but you can't divide a string, right? Like you can't say my name is Hayden divided by Lachlan. Like you can't say that. Similarly, a const iterator does not have an assignment type. It does not have other types that imply mutation because it's read only. So that's what this error means. It says no viable overloaded equals, basically saying that it has no idea how to take this type here, which is a const string, because that's what it gives you. Like when you dereference the iterator, it gives you a const version of the data type. And therefore you can't do it because the compiler's like, I don't know how to actually set a const string to be something else. So yeah, that's what that is. And you can see VS Code's picking up on that too. Anyway, you can, so const prevents mutation at compile time. It doesn't do anything during runtime because it won't let you compile because it can tell if you're going to mutate something at compile time. The other thing to note about it is that some people ask, oh, when should it be const or not? Well, it's like a normal const. If you're not modifying it, you should make it const. Now, a couple things with that. The reason we like to do that is because it makes it really clear to other programmers what your intentions are. So if you say cbegin, it's clear to someone that you don't want someone to mutate this while you're iterating through it. And then similarly, I think there are some instances where compilers will be able to do things faster if they know it's const. I don't know the specifics of that, but I've also heard people tell me that that's a bit of a red herring because most compilers, even if you define something as not const and you don't modify it, the compiler will actually set it to be a const iterator anyway. So I've heard people tell me that the compiler in this case will just be like, nope, it's not being modified. We'll just make it a const iterator. Nice and simple. Great. Last thing here is stream iterators. So this one wasn't really an example. This was something that we were going to throw out, but I wanted to keep it because it was just kind of random. I think we need to make a file called data.in, but you can iterate through input streams and output streams and input file streams. So like you've probably gotten a sense in C++ of these things called streams, which are just how you sorry, I was just reading something. It's a really good question. I'll come back to that in a sec. But yeah, basically, when you open a file as well, which is essentially a stream, like, imagine opening a file. It's not like you don't copy the whole file into memory. It's like you have a pointer to the beginning of the file, and then you iterate through the file till you get to the end, right? And similar thing here, you can iterate through this by, it's like, let's try this out. I didn't want to do this one, but I've changed my mind. So if I make a file called data.in, maybe just like 1, 2, 3, 4, 5 or something, I don't know. Let's try that. Let's try and compile this. This might go against me. Oh no. Okay, that's not what I hoped would happen. Maybe I should have deleted this one instead. It's probably because I'm running it from the wrong directory. Let me try that. Maybe that's the problem. Okay, well this seemed to work. Let's try putting spaces there. So, right. So let's have a look at what this is here. iStream iterator int begin. Now, I don't want to get into this whole stuff because I don't think it's that relevant, but essentially an input file stream is a stream here, and then we're trying to create an iterator from it, which it's kind of like this type here. This is just the thing is, this is just very tangential to all the other stuff we're doing. But if you just kind of take the code at surface level, we're creating an iterator here, a begin iterator for an input stream, and we're creating an end iterator for an input stream. Now the begin iterator actually needs the stream, because otherwise it doesn't know how to do anything. And what you can see here is that we are printing the first character 1, and then we're incrementing it. So this is a post increment, so we print it, and then we increment it. Then we increment it again, but we don't do anything with it, which is why the 2 isn't printed out. And then we increment it again to get the 3 after we print it out. And then we have a while loop that will just keep going while the iterator at the beginning is not the iterator at the end. And it will just keep printing it out. Now some people are probably like a bit confused here, but like if I could just say rewrite the structure for you, I could say something like this instead. I could say like, iStream iterator begin as that, and then I could say, you know, auto it equals begin. That's basically what happens in the other cases, and then I could just use the iterator here. So this might be more visually clear to people. What's happening is like, just like in the for loops we had here, you know, we get the begin iterator, we get the end iterator, and then we have our iter or our it, which is what we're using to loop through it. And then this should still compile. That wasn't the file. Yeah, so that should still work there. So there's a lot of things you can do with iterators. End is like end of file. Yeah, that's correct. Now, Charlie asked a great question. You can change the begin variable name, yes. These are just variable names. Sorry, so just to really maybe explain this some more, because I'm seeing more questions about it. This is a default constructed iStream iterator, which will always be equal to the value of end. This is a constructed iStream iterator that's given the actual input stream. So if you didn't put the in there, then it would just be another end iterator, even if you just called it begin. Now the I completely forget what I was going to say. Oh yeah, Charlie asked a great question, I think. Yeah. So let's go back to the previous example, because I want to just chat about this a tiny bit more. Charlie asked a great question, which is like, why is this auto iter when we use cbegin? Because we know for a fact that if we want something to be const, auto strips the const away. So if the right-hand side of an assignment is const, like cbegin, then shouldn't we add it to the left, because the auto will strip it away? And the answer is no, because the actual type that a cbegin returns is a const iterator, in the sense that it's not a, like, the type is not a const iterator. The type is a const iterator, which is just another type. Like, the two types are iterator and const iterator. They're not like, there's no const version. They're just two non-const types that one has const in the name. And the reason that's important is because iter itself is not actually const. If it was const, it wouldn't compile. Because this, like, we could try it, right? Like, if I actually tried to make this const, it would fail to compile, because the compiler would see that we're trying to increment it. And it would see all my bullshit. Yeah, so the output here is cannot increment value of type const blah 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 blah. So yeah, so essentially the actual iterator itself is not const, it's just the type of this non-const iterator ensures that when you dereference something, that what you dereference is a const type. So the actual iterator here is still non-const, it's just that this iter here has a type const string. And if this is a non-const iterator, then the iterator dereference has a type of string. So it really affects what the type of the dereference of the iterator is, if that makes sense. So yeah, that's the relevance, essentially. Is there a type of operator? Probably. I don't know, I haven't really used one. Do they have type of in? Try it out. See what happens. Maybe not. I don't know. I'm just trying this. It probably doesn't work. Nope. Is it decal type? But I think decal type's a type. No, decal type's value to a type. How do you go value to a... How do you do type to value? Type ID. Type ID expression. What does that actually return, that function? Hopefully it returns a string or something. I don't know, let's just try it. Type ID of iter. Is that built into the language? I'm not sure. I'm worried. I maybe won't go down this rabbit hole. Type def's a different thing. No, I don't know anything about this, so... I'm not going to get lost in it. Oh, type info name. I mean, we could try something like this. Oh, standard cout. Standard type info of iter dot name. Maybe. Then we have to hash include type info. I don't know if this will work. If this doesn't work, I'm going to give up. Even if someone tells me the right answer. Type ID var name. Sure, okay. That's alright. I might leave this one alone. Yeah. Ah, alright. You guys tell me. Only because we're running quite ahead on this lecture, but if this doesn't work, I'm out. I'm out. Nope. Good job. Good job, everyone. Let me do 204 again. Oh, I see. Okay. I've always wanted an NST3111 Rapida IPNS. You can see basic string there, but I guess if we make it a const iterator, we might see this change slightly. I guess that's the hope. Maybe it'll give us like a better name, like, what are we, const iterator? There's a K there. K for const, I guess. Let's just pretend that K's for const. Cool. Alright, so that's pretty much it on iterators. The last thing on iterators that I did want to chat about is back to our actual container slides, because in the containers code we had this map example here. And I want to show you another way to like look up if something's in a map. So for instance, here I could say if m.contains cat, then standard cout is there, or something like this. Else standard cout is not there, like that. Yep, could do something like this, and if I build and run that one, it'll tell us whether cat's in there. Back to 3. So yep, it's there, cat's in there. That's all correct. The other way that you actually do this is that most containers have a find function where you can say auto iterator equals m.find, and then you can pass in the key or the value that you're looking for, and then you say if iter is not equal to m.end, that means it's in there. And then you do a similar thing here. So what you're so how this works is that, and we're going to talk more about this next lecture, is that a find function returns you an iterator to the value, and if it can't be found, it returns you an iterator to .end. So in this case, it could be found, so it returns an iterator to the value. Otherwise, it returns it to .end. So that's kind of similar to at. I guess the difference with at is that... Okay, this is actually a really interesting thing. Good thing we're about to wrap up, because we can waste time on this. So let's compare 3 methods, or 2 methods, I guess, is probably, or 3. Yeah, let's do 3. So the first one is using the iterator. The second method is we're going to do a what we did before, which I shouldn't have deleted, which is that if m.contains cat, then we want to say print it out. And that's how I'm going to modify this too, is I actually want to print out the cat. Like this, say like cat is there. But in this case, if it contains cat, I'm going to use m.at cat. And then let me just delete this. So I've actually buggered this explanation, so let me try again for you. Sorry guys. So what I'm doing is I want to look through this map to see if cat's in it. And if cat's in it, I want to print the value. So what I'm actually going to say here is value at cat, which is the key. I'll just say value. Screw it. This will be easy. Keep this really, really easy. So if cat is in there, I want to print out 10.157, right? Bam. If cat's not in there, I want to say it's not in there. In this one, I say m.contains cat, and then I say if it's in there, I want to print m.at cat, or I want to print what I had up here, which is value is what's at cat, right? Because when you look things up by a key, you get the value. Now, Quinjian says that iter dereference will return a pair. Yes, you're right. I probably should have like thought about that. So I'll say key value equals iter, and then I can do key value dot second. So what actually happens with maps, which is kind of interesting, I don't know if it's dot second, I can't remember, is that when you dereference an iterator to a map value, it doesn't give you the value, it gives you the key value pair. So what this will actually do is it'll actually give me a cat 10.157. So we actually have to pull that into a standard pair. That's what this is. And then we get the second element from that. A little bit roundabout, a little bit ugly, but it works the same. Then we have this one where we look up whether the cat's contained in the map, and if it is, we get the value at the key cat. And this we could only do from C++20, because before that we didn't have .contains. And then what we would do before C++20, if we wanted to avoid iterators, is we would... I will fix that up. Let me get back to that line. Is before C++20, we would actually probably have to say, like, try to do this. Oops. We might have to say try to do that, and then otherwise we would say catch standard exception. I think you can do catch all. We'll come back to exceptions in week 4, and then we do that. So it's kind of like, because previously the only way to actually like tell if it wasn't in there was to try and get it, and then it would throw an exception. I think they're kind of the 3 ways to do it. So let's first get this compiling. Compiled, great. And now you can see here that it says I got the 3 values, which means all 3 of these things work. Now, what is the difference between these 3 things? Now, naturally, this one has exceptions, which makes it kind of awful and ugly. Exceptions are generally something I guess you'd want to avoid if you could, because they disrupt the logical flow of your program, and they're a bit, I don't know, it's just a weird thing to use an exception for. So this one makes more sense. I think the downside with this one, though, is that map, as you know, is an ordered associative container, which means that a lot of its performances are like log n. So for me to actually look that up, I actually have to do 2 lookups here. So there's actually a cost to look up, and then I have to look it all up again, because these 2 things aren't talking, right? They're 2 separate statements. Whereas using the iterator, I'm actually able to look it up once, and then I've got an abstract pointer to that value I found, and then I can use it. So in a lot of ways, this is actually quicker than the contains one, because you're only having to do 1 lookup. Could I use m.count inside the if condition? I guess so. I'm not sure. I don't see a reason why you wouldn't. Yes. Oh, yes, so that's the other thing. I really like this point. So I've simplified this a little bit just to explain a point. And Shaloya has pointed out a really good thing, which is that if you actually go and look up standard map, though, right, one of the other differences here is that standard map, if you look at the, let's look at the time complexity. So at has a complexity of logarithmic, which makes sense if it's a tree. Contains will probably have the same thing, I guess, wherever contains is. Contains will have a complexity of logarithmic. But when we look at find, what's find going to have? Logarithmic. So this is interesting because find is logarithmic, which makes sense because you're essentially delegating it to the container. If you were to try and use an iterator, though, to find it, like a .begin.end, a .begin.end is actually asking for you to linearize the entire structure so you can move through it linearly. So it would actually be quite slow to go through it with .begin and .end. That would be a worst case ON because you have to do n operations through it. But in the case of find, you're not actually asking it to give you a linear representation of the container. You're actually just saying, you go find it however you think works, and just give me an iterator to where it is so I can use my iterator semantics. And that's a great example too, because we'll actually talk about that tomorrow night when we talk about algorithms, because the find algorithm is actually slower than the find method, which will hopefully really consolidate that idea. Anyway, it's 7:50 and pretty much out of content, even though this was fun to go through. So tomorrow we're going to go through iterators. I won't lie, I totally forgot that there's a public holiday in week 4 on the Monday. So we will probably have to do operator overloading week. The next few topics might end up over multiple lectures, if that makes sense. So we might be doing a lot of part 1, part 2 lectures, which is fine. Last question. Alan says, what is the point of returning the iterator rather than a reference to the object itself? Well, I mean, we already have that with at, right? And there's no other way to really... There's really no way to do like a reference lookup that doesn't have an exception without making two like function calls. But the reason that iterators are useful here is because, well, it's what I just said. You can check and look it up in one function call, but also sometimes you want to do something like go to that point and then loop through the next 3 values, for instance. Or maybe you want to find all the values in a container that are whatever. Like it's an iterator is like you're reaching your hand into the container and holding it at a certain point, and you can do a lot of things from there. You can go forward, you can go back in some instances, you can mutate it. Like, I mean, you can do that with a reference too, but there's a bunch of little things you could do with it. When you want to loop through structures, it's pretty much like you use a for each loop, a for range loop, which actually uses an iterator, to be honest. Surprise! So these loops here actually use the iterator. It won't, like, that's all it does. That's actually all it does. Which makes sense, because like, how the hell does it know how to move through that array? Like, you know, this doesn't just magically figure it out. It has to use the iterator to figure it out. And that's probably why you can use this structure too on like maps and stuff, because I think it just uses the .begin .end stuff for you. But generally speaking, my point is you're not actually going to loop through things that much like this, because you probably loop through it like this. The main value of iterators is in more complex stuff, and it's also like for things like find. And I don't think you're not going to use a ton of iterators in assignment 1, probably. I haven't done it in years, so I don't know off the top of my head. But you probably use the find one a little bit, I would guess. There'll be a few of you probably use find a bit. Would it be bad practice to use contains? No. I don't know if any of you are actually using an ordered map or not. But unordered sets, you would probably just use .find if you need the value. If you don't need the value, just use contains, because it's cleaner. But if you do need the value, then you'd probably want to use find, because then you save yourself 2 lookups, which could be costly. Okay, 7:54. I'll see you all tomorrow night, and thanks for the fun time. That's pretty much it on iterators. Tomorrow we'll do the last part of STL, which is algorithms, and we'll tie it all together. So thanks everyone for being such charming participants as always, and I will see you tomorrow. Have a good day. Try not to be too cold. It's cold. It's winter. Sucks. But